Hey guys, here is 10.1, the tangent notes. This is only about 2 theorems, and all the terms I did not make a video for. You'll just have to get the notes, okay? I'm going to be better about writing larger so that it's easier for you to see. First thing is, look at the picture. We're going to talk about a tangent. Both of these refer to a tangent. If you'll remember from the terms, if you have a circle, a tangent touches the circle only exactly at one point. Exactly one point. That point is called the point of tangency. So right here, P refers to this point. P is called the point of tangency. Line M, this is italics M, okay? So it is not a capital, it is not a point. M is referring to the name of this line. M is the tangent. The statement says, line M is tangent to circle Q. If and only if, I'm going to explain this in a second, line M is perpendicular to the radius QP at this point P, okay? So M, if M is tangent, it's going to be perpendicular to the radius. If it's a tangent, it's perpendicular. If it's perpendicular, it's a tangent. This phrase, if and only if A, then B, and if I switch these two and say if B, then A, this is called if and only if. If it's a tangent, it's perpendicular. If it's perpendicular, then it's a tangent. It goes in both directions, okay? Let's write this in words over here. First, this situation, a tangent, is always in the same plane as a circle. So we're going to say in a plane, a line is tangent to a circle if and only if. If and only if, okay? The line is perpendicular to the radius. This line has to be perpendicular, right? Perpendicular to the radius. Well, to any radius. I'm going to say to a radius. To a radius, and it has to be perpendicular to the end point on the circle. At its end point on the circle. Okay, so every time we do this, we are going to draw a right angle at point of tangency. So always draw the right angle at the point of tangency. And we're always, not always, but mostly going to use, okay, leg squared plus leg squared equals hypotenuse squared. You're going to use the Pythagorean theorem a lot on using this kind of problem. Okay? So whenever we talk about point of tangency, think of a right angle with the radius and the tangent itself. Okay, that's the first one. We only have 2. Okay, the second one. This one I'm going to explain, but here's the gist of it. If you have a tangent if you have a point outside of a circle, external to the circle, so we have point S, we draw the tangent, we draw the tangent. These tangents are always going to be the same length. That's all you have to know. If we have a point outside of a circle and we draw the two tangents from that point, the tangents will always be the same length. So I'm going to say tangent segments from an external point are congruent. If you remember, congruent just means same length if you need to write that word. Every one of these problems is going to be a part equals part problem. Okay, I am going to show you quickly why they're congruent. You don't have to do this, I'm just showing you why. Okay, I'm going to draw in each radius. We know at the point of tangent C is a right angle, because that's what it means to be tangent. And I'm also going to draw in segment PS. If you look at this, you've got two right triangles. The diameters in a circle are always congruent. So this, not diameters, radius. This radius is the same length as this. So these two radii are congruent to each other. This segment is shared between this top triangle and this bottom. So by reflexive, this triangle up, this segment is congruent to itself by reflexive. And we could see we've got this triangle here, we've got this triangle. If you use HL, hypotenuse leg, the triangles are congruent. Because the triangles are congruent, these segments are equal to each other, equal lengths. Okay, that's why, if you care why. Okay, I'm going to do a couple. Oh, and remember, every one of these will be a part equals part. Okay, let's do this one. Is segment ST tangent to circle P? If it is tangent, then there'd have to be a right angle, right? If tangent, then you'd have to have this perpendicular, this right angle right here. Okay? If this is a right angle, that would mean that this would have to be a right triangle. Okay? So if it's a right triangle, if you're testing to see if it's a right triangle, you're going to go the long side squared has to equal the short side squared plus the short side squared. If you want to think hypotenuse squared has to equal leg squared plus leg squared. That's what we're thinking. So we're going to check this. This would have to be a leg. The short sides and the long side would have to be the hypotenuse if this were true. So I'm going to check 37. So we're going to check, is this true? Is it equal? So does this hypotenuse, the long side, equal the short side squared plus the short side squared? And if it does, if yes, then this is a right triangle, and this would be a tangent, segment ST. That's how you're going to do number one. You're going to test it. Is this true? Okay? So that's how you do that one. Number 4 is very, very similar. 4 is harder because it doesn't. Number 1, okay, on number 1, this length, 35, they tell me this whole length is 35. This whole length is 12. And it tells me 37 goes from S all the way to P. Okay? I'm going to jump to number 4. This one says, is segment DE tangent? If it's tangent, this would have to be a right angle. And if it's a right angle, then this would have to follow the Pythagorean theorem. Okay, we'd have to go leg squared plus leg squared equals hypotenuse squared, or think short side squared plus short side squared equals the length of the long side squared. Problem is, 3 goes from here to here. My radius equals 3 long. 4 is from here to here. 2 is only from here to here. 2 goes from point of intersection to E. I know my radius is 3. If 3 is here, my radius, then this radius is also 3. Okay? Which means that length from C to E, right, would have to be 3 plus 2, which is 5 long. Okay? So if this is going to be a right triangle, we're checking. I'm going to redraw it over here. This would be 3. There's my right angle, 4, and 5. Short side squared plus short side squared equals a long side squared. Is that true? If it is true, then this is a right triangle. Okay, so you have to get this part to do it. I'm going to do number 2 very slowly with you. Number 2 is hard. Okay, again, we know the radius has to equal the radius. Within a circle, the radius is always the same length. If this is 5 long here, the radius would be 5 long here, would be 5 long here. Every radius that I draw would be 5 long. Within a circle, the radii are all the same length. That's why we said if this length is 3 for the radius, then this length would be 3 for the radius. If this length is r for the radius, then this length would be r. Down here, we said to get the whole entire length, we added 3 plus 2. This whole length is 5 long. If I want to know how long something is, I add the 2 parts together. That gives me the whole length. So on this one, I would have to add 50 plus r to get this whole length, which gives me hard algebra. Okay, let's read the question. In the diagram, B is a point of tangency. It is a point of tangency, so we're going to draw the right angle in there. We're going to draw that in right here. Since B is a point of tangency, it has to be a right angle. The box always points to the legs, so this is a leg, and this is a leg, and this side here then is the hypotenuse. Okay, there's my H. So hypotenuse squared equals leg squared plus leg squared. Either way, or leg squared plus leg squared is hypotenuse squared. However you want to do that. Okay. This hypotenuse from A to C, okay, that whole length is 50 from here to here, r from here to here. So 50 plus r is the whole length. Okay, I did a capital R. Maybe it's easier to see. Okay, let's do it. So 50 plus r squared equals the length of the leg squared plus this leg here, I'm just calling it r. Now, this is going to require some review. If you need help, more help, come in during class. 50 plus r squared does not mean 50 squared plus r squared. That is wrong. Okay? Does not work. This means 50 plus r times 50 plus r. We go first times first, outside times outside, inside times inside, last times last. Then we add like terms. Like terms, this has an r and an r. The exponents are only 1. This exponent's 2. To be like terms has to be the same variable with the same exponent. So we're going to add these. Okay? So this is everything on the left side of the equation. I still have to fill in the right side. So I'm going to do it right now. Oops, 80 squared plus r squared. Okay, we could go ahead and subtract r squared from both sides. So that'll just cancel out. So now we have left 2,500 plus 100r equals 80 squared. 8 times 8 is 64, and they add the 2 zeros. I need to get the r isolated, so I have to get rid of 2,500 from both sides. I've got 100r equals 3,900, and then I'm going to divide by 100. So I get r equals 39. Okay, let's look back at my question then. That would be, this is 39 long, this is 39. So the whole thing, 50 plus 39, would be 89 long. So I got 39, 89, and 80. I could square those, see if it works, it will. And then I know if I did it right. Okay, that's number 2. Okay, one more problem, then we're done. When I look at number 3, it says segment RS is tangent to circle C at point S. Segment RT is tangent. This refers to this picture here. If I have a circle and an external point, these two tangent segments, if they're both tangents from one point, are going to be equal to each other. Remember we said this is a part equals part problem. So this length, R to S, is equal to this length from R to T. This is simply 28 equals 3x plus 4. And then you solve for x. When you flip this over on the back, you have more, the problems are similar, so you get to practice the same skills, and then you get to practice some more of your terms, okay, from the first part. That's it. Good luck. If you need more help, come in and get help.